Welcome to Farmtips Diary. A century ago, farmers grew hundreds of different crops adapted to local climates and traditions. Today, just 3 plants feed most of humanity. This is the story of how our crops transformed, what we gained, what we lost, and what the future of food diversity might look like. The rise of the Big Three? Walk through any major agricultural region today, and you'll see endless fields of corn, soybeans, or wheat. These 3 crops, along with rice, now occupy more farmland than all other food crops combined. But rewind 100 years and the landscape looked dramatically different. Fields were patchworks of diversity. Farmers grew dozens of crop varieties, each selected over generations to thrive in specific conditions. So what happened? How did we go from agricultural biodiversity to monoculture dominance? The answer is a combination of economics, politics, and plant science that reshaped the entire planet. Corn's rise is perhaps the most dramatic. In 1925, American farmers grew corn primarily to feed livestock and for human consumption as cornmeal. Yields averaged around 25 bushels per acre. Today, that number exceeds 170 bushels per acre in the United States. This 7-fold increase didn't happen by accident. It was engineered through decades of selective breeding, hybrid development, and eventually, genetic modification. Corn became king because it's astonishingly versatile. It feeds cattle, pigs, and chickens more efficiently than almost any other crop. It converts into ethanol for fuel. It's processed into high-fructose corn syrup that sweetens everything from bread to soda. Cornstarch, corn oil, and hundreds of industrial products trace back to this single plant. The modern food system is built on a foundation of corn. Soybeans followed a similar trajectory, but for different reasons. Nearly unknown in Western agriculture before 1920, soybeans arrived from East Asia as a curiosity. By the 1940s, they were recognized as a protein powerhouse. Soy meal became essential livestock feed. Soy oil filled bottles in every kitchen, and as global meat consumption exploded, soybean production skyrocketed to meet the demand for animal protein. Today, soybeans occupy more than 100 million hectares worldwide. Brazil and the United States alone produce nearly 2/3 of the global supply. This expansion came at enormous environmental cost. Amazon rainforest and Cerrado grasslands were cleared to plant soy, but from an agricultural perspective, soybeans are nearly perfect. They fix nitrogen from the air, enriching soil for the next crop. They thrive in diverse climates, and they provide both protein and oil in one package. Wheat's dominance is older, but equally dramatic. As a staple grain for thousands of years, wheat was already important in 1925, but the Green Revolution transformed it from a regional crop into a global lifeline. Norman Borlaug's semi-dwarf wheat varieties turned Mexico from a wheat importer to an exporter within a decade. These varieties spread to India and Pakistan, averting famines that could have killed millions. Modern wheat is shorter, stronger, and more responsive to fertilizers than its ancestors. It resists diseases that once devastated harvests. It matures faster, allowing multiple crops per year in some regions. Wheat feeds more people directly than any other crop, forming the basis of bread, pasta, noodles, and countless other foods across every continent. The rise of these 3 crops wasn't random. They won because they met the needs of industrial agriculture. They respond well to mechanization. They store and transport easily. They scale efficiently. And perhaps most importantly, they fit into the economic and political structures that shaped 20th century food systems. Government subsidies, commodity markets, and trade agreements all favored crops that could be grown in vast quantities and moved globally. The science of transformation. Behind this agricultural concentration lies a century of plant science that borders on miraculous. Early 20th century farmers selected seeds from their best plants, saving them for next year's planting. This traditional breeding had shaped crops for millennia, but moved slowly. Each generation required a full growing season. Improvement was gradual and limited by whatever genetic variation existed within a species. Then came hybrid breeding. Scientists discovered that crossing 2 genetically distinct parent lines produced offspring with hybrid vigor, growing faster and yielding more than either parent. The catch was that saved seeds from hybrids performed poorly, forcing farmers to buy new seeds each year. This shift from seed saving to seed purchasing transformed agriculture into a market-dependent system, but the yield gains were too compelling to resist. Corn hybrids arrived in the 1930s and swept across the American Midwest within 2 decades. Yields jumped 20 to 30% almost immediately. Similar breakthroughs followed for wheat, rice, and other major crops. Plant breeders became heroes of food security, and their work accelerated throughout the century. By the 1960s and 70s, breeding programs focused on specific traits. Disease resistance became paramount as monocultures made crops vulnerable to epidemics. The Irish potato famine of the 1840s remained a haunting reminder of what happens when genetically uniform crops face a pathogen they can't resist. Breeders raced to introduce resistance genes, staying one step ahead of evolving pests and diseases. Nutritional improvement also entered the picture. Golden rice, engineered to produce beta-carotene, aimed to combat vitamin A deficiency in regions dependent on rice. High-lysine corn addressed protein quality issues. Iron biofortified beans tackled anemia. These biofortified crops represented a shift in thinking from grow more food to grow more nutritious food. Then came the genetic revolution. In the 1990s, scientists learned to insert genes directly into plant DNA, bypassing the slow process of traditional breeding. The first genetically modified crops were simple by today's standards. Bt corn produced a bacterial protein toxic to specific insects, reducing the need for insecticide sprays. Roundup-ready soybeans tolerated glyphosate herbicide, simplifying weed control. Farmers adopted these GMO crops faster than any agricultural technology in history. By 2020, over 90% of corn, soybeans, and cotton grown in the United States were genetically modified. Globally, nearly 200 million hectares of GMO crops were planted annually. The reason was pragmatic. They worked. Yields increased, labor decreased, and in many cases, chemical use dropped. But genetic modification remains controversial. Critics worry about corporate control of seeds, environmental risks, and unknown health effects. Proponents point to decades of safe consumption and environmental benefits like reduced insecticide use. The debate often misses a key point. GMOs are a tool, neither inherently good nor bad. Their impact depends entirely on how they're designed and deployed. Today, gene editing technologies like CRISPR are opening new frontiers. Unlike older GMOs that introduced foreign genes, CRISPR makes precise edits to a plant's existing DNA. This creates crops that might have evolved naturally but would have taken centuries. Drought-tolerant wheat, heat-resistant rice, tomatoes with longer shelf life. The potential is vast, but so are the ethical and regulatory questions. The vanishing variety. While yields soared and major crops dominated, something quieter and more troubling was happening. Crop diversity was disappearing. In 1900, farmers in the United States grew thousands of apple varieties. Today, just 15 varieties account for 90% of production. Similar losses occurred worldwide and across all crop types. This erosion of diversity happened gradually, almost invisibly. As hybrid seeds and green revolution varieties spread, traditional landraces were abandoned. A landrace is a locally adapted variety maintained by farmers over generations. They might not yield as much as modern hybrids, but they carry genetic traits for drought tolerance, pest resistance, or nutritional quality that commercial varieties lack. When a landrace disappears, it takes thousands of years of evolution and selection with it. That genetic information is irreplaceable. And we're losing it fast. The Food and Agriculture Organization estimates that 75% of crop genetic diversity was lost during the 20th century. 3/4 of our agricultural heritage vanished in a single human lifetime. Why does this matter? Because diversity is insurance. The Irish potato famine killed 1 million people because Irish farmers relied on a single potato variety. When blight struck, there were no resistant alternatives. Modern agriculture faces the same risk on a global scale. If a disease or pest evolves to attack the handful of crop varieties feeding billions, we could face catastrophe. Diversity also represents future potential. Hidden within rare and forgotten crop varieties are genes for climate resilience, nutritional richness, and productivity under stress. As climate change reshapes growing conditions worldwide, we'll need to breed crops that can handle heat, drought, floods, and unpredictable weather. The raw material for that breeding exists in seed banks and traditional farms, but only if we preserve it. The irony is sharp. We've never had such powerful tools to improve crops, yet we've narrowed the genetic foundation to a dangerous extreme. It's like having an incredible library but burning 75% of the books. The remaining 25% might be bestsellers, but they don't contain all the knowledge humanity needs. Some efforts are underway to reverse this loss. Seed banks around the world, including the Svalbard Global Seed Vault in Norway, preserve millions of seed samples in long-term storage. These are genetic Noah's Arks, protecting crop diversity against future catastrophe. But seed banks are passive. Seeds sit frozen, disconnected from the evolutionary forces that shape living populations. A more dynamic approach is conservation through use. Farmers who continue growing traditional varieties keep those genetics alive and adapting. Organizations promoting heirloom tomatoes, ancient grains, and heritage livestock breeds create markets that make diversity economically viable. When people buy purple carrots, multicolored corn, or einkorn wheat, they fund the preservation of genetic variety. The globalized field. Crop transformation over the past century cannot be separated from globalization. What farmers plant is no longer determined solely by local soil and climate. It's shaped by international trade, consumer preferences thousands of miles away, and market forces that span continents. Consider the soybean boom in South America. Brazilian farmers didn't start growing soybeans because they suddenly needed more tofu. They planted soy to feed chickens and pigs in China. As Chinese incomes rose and meat consumption soared, demand for animal feed exploded. Brazilian farmers responded by converting vast areas to soybean production. The result is that land use decisions in the Amazon are driven by dietary choices in Beijing. Or look at quinoa in Bolivia and Peru. For thousands of years, quinoa was a subsistence crop for Andean farmers. Then Western consumers discovered its nutritional profile, and quinoa became a global superfood. Prices skyrocketed. Andean farmers shifted from diverse crop rotations to quinoa. Ironically, as quinoa became too expensive for many local people, the crop's traditional guardians could no longer afford to eat it. Globalization also accelerates crop uniformity. International commodity markets favor standardized products. A food processor in Europe buying wheat doesn't want 50 different varieties with varying protein content and milling characteristics. They want uniformity, predictability, and scale. This drives farmers worldwide toward the same narrow set of commercial varieties. Trade agreements reinforce these patterns. Subsidies in wealthy nations allow their farmers to sell corn and wheat below production cost, undercutting farmers in developing countries. Those farmers then switch to export crops like coffee, cocoa, or palm oil to earn foreign currency. Traditional food crops are abandoned in favor of cash crops, making communities dependent on global markets for basic nutrition. Consumer preferences also reshape fields. The demand for year-round produce in supermarkets drives monoculture production in regions with favorable climates. Almonds in California, avocados in Mexico, and berries in Chile grow in vast plantations serving global markets. Local food diversity declines as farmers specialize in whatever sells internationally, yet globalization isn't purely negative. It also spreads beneficial crops and knowledge. High-yielding rice varieties developed in the Philippines improved food security across Asia. Drought-tolerant maize from Mexico helps African farmers cope with unreliable rainfall. Open-source seed-sharing networks allow farmers worldwide to access genetics that might save their harvests. The challenge is finding balance. How do we enjoy the benefits of global trade and knowledge sharing while preserving local diversity and food sovereignty? How do we ensure that crop choices serve both farmer livelihoods and community nutrition, not just export earnings? The next century of crops. Looking forward, the next 100 years of crop evolution will be shaped by forces both familiar and unprecedented. Climate change is the most obvious disruptor. Rising temperatures, shifting rainfall patterns, and extreme weather events are already affecting crop performance. The varieties that fed the 20th century may not thrive in the 21st. Scientists are racing to develop climate-resilient crops, heat-tolerant wheat that maintains yield and temperatures that would shrivel current varieties, flood-tolerant rice that survives 2 weeks underwater, drought-resistant corn that produces grain with half the usual water. These aren't science fiction. They're in development now, combining traditional breeding with genetic technologies. We'll also see crops designed for changing diets. As concerns about health and sustainability grow, demand is shifting from calorie-dense staples toward nutrient-rich vegetables, legumes, and novel proteins. This could diversify production, but only if farmers find it profitable. Markets and policies will determine whether nutritional diversity replaces commodity monoculture. Alternative crops that were forgotten or underutilized may return. Perennial grains that grow back year after year without replanting could reduce erosion and labor while sequestering carbon. Indigenous crops adapted to marginal lands might feed communities as conventional agriculture struggles with climate impacts. Seaweed and algae could become significant food and feed sources. Technology will enable precision breeding at speeds unimaginable today. Artificial intelligence will predict which genetic combinations produce desired traits. Gene editing will fine-tune crops for specific environments. Vertical farms and controlled environment agriculture will grow crops independent of weather and seasons, though at higher energy costs. But technology alone won't determine crop futures. Social movements advocating for agroecology, organic farming, and food sovereignty are pushing back against industrial monoculture. They argue for diversity, local adaptation, and pharma control over seeds. This tension between high-tech industrial agriculture and alternative food systems will shape the next century's fields. Consumer awareness is growing. People increasingly question where food comes from and how it's grown. Farmers markets, community-supported agriculture, and heritage variety. Enthusiasts create niches for These alternative markets are small compared to industrial agriculture, but they preserve options and knowledge that might become critical. The biggest unknown is whether we'll learn from the past century's mistakes. Will we continue narrowing crop diversity until a crisis forces change? Or will we proactively maintain the genetic insurance that diversity provides? Will we breed crops that enrich soil and support ecosystems, or only focus on yields? Will we ensure farmers worldwide can access seeds and knowledge, or allow concentration of control? Collaboration for the future. The future of crops isn't predetermined. It will be shaped by choices made by farmers, scientists, policymakers, and consumers. Each group has a role to play in protecting diversity while meeting human needs. Farmers are the front line. Those who maintain traditional varieties, experiment with alternative crops, and share seeds preserve living genetic libraries. Supporting these farmers economically and honoring their knowledge is essential. Farm policies should reward diversity and soil health, not just commodity production. Scientists must balance productivity with resilience. Breeding programs should maintain broad genetic bases rather than narrowing to a few elite lines. Open-source approaches to crop improvement can democratize access to innovation. And research funding should support orphan crops and minor species, not just the big three. Policymakers shape incentives that drive crop choices. Subsidies, trade rules, and research priorities all matter. Regulations should encourage innovation while ensuring safety. Intellectual property rules must balance innovation rewards with farmer rights to save and share seeds. Conservation programs need adequate funding. Consumers drive demand. Choosing diverse diets, supporting local farmers, and valuing quality over just price sends signals through supply chains. Every purchase is a vote for the kind of agriculture we want. Buying heirloom tomatoes or ancient grains funds their continued existence. The goal isn't to return to 1925. Modern crop science has given humanity incredible tools to feed billions sustainably. The challenge is using those tools wisely, maintaining the diversity that underpins resilience while embracing innovation that addresses real challenges. We need both cutting-edge genetics and ancient landraces, both global trade and local food systems, both productivity and sustainability. History teaches that crops evolve in response to human choices. The past century narrowed diversity, but increased yields. The next century must do both. We must produce enough food for 10 billion people while preserving the genetic resources that make future adaptation possible. That's the challenge. And unlike the challenges of 1925, we now understand what's at stake. Recap. In 100 years, a handful of crops came to dominate global agriculture. Corn, soybeans, and wheat rose through a combination of science, economics, and policy. Selective breeding and genetic modification increased yields dramatically, transforming these plants into hyper-productive versions of their ancestors. But this success came at a cost. Crop diversity collapsed, with 75% of agricultural genetic variety lost. Globalization reshaped what farmers plant, driven by distant markets and consumer demands. Meanwhile, the tools to modify crops have never been more powerful, from hybrid breeding to CRISPR gene editing. Looking ahead, climate change and growing populations will demand crops that are both productive and resilient. The next century could see forgotten crops return, novel breeding technologies accelerate, and hopefully a renewed commitment to diversity. The future depends on farmers maintaining traditional knowledge, scientists developing climate-resilient varieties, policymakers creating supportive frameworks, and consumers valuing diversity. We have the tools to feed the world sustainably. The question is whether we'll use them with wisdom learned from the past. If this exploration of crop evolution resonated with you, give this video a like and share it with anyone who cares about food, farming, or the future. Subscribe to Farmtips Diary for more deep dives into the forces shaping agriculture, and don't forget to hit the notification bell so you catch every new video. Thanks for watching, and we'll see you in the next one.